Hello everyone, welcome to a series on binomial coefficients. This is some of my favorite math, personally. I'm excited to share it with you. It'll be a pretty short series just covering the main highlights of this topic along with some applications as we go. So let's just jump into it. By the way, the only prerequisite really is high school math. I'm not going to assume any university level math. We will use calculus at one point, but that part is totally optional. Other than that, just be comfortable with the basics and you'll be okay. So I want to motivate this with an example. Say you are forming a student council consisting of 3 students, and there are 5 nominees to choose from. How many different councils can you make? Okay, it seems like a pretty practical question, but without binomial coefficients, we don't really have a great mathematical framework for answering this. Well, let's just answer it by brute force. So let's say our 5 nominees, will label them A, B, C, D, and E. And let's just manually check how many different councils we can make. And by this I just mean let's just take 3 of the letters here and make councils with them. And the order doesn't matter. So let's just list some off. Well, we have ABC, we have ABD, we have ABE. Those are all the possible ones with A and B in them. Now let's take A and C. So we already covered ABC, so we don't include that. We can include ACD, we can include ACE. And now the only other thing that we haven't gotten with an A is ADE. Okay. Now let's look at all the ones that we can do without A. So we have BCD, we have BCE. That's all the ones we can do now with just B and C. Now we have CDE. And we have BD as well. And I believe that is all the possible combinations that we have. Okay, so this is all the councils we can make. So our final answer, just counting this up, is 10. Okay, 10 different councils that we can make. So, okay, that was kind of painful. It would be nice if we had a better framework for answering this kind of question. And that's exactly what we're going to develop in this series. A framework for answering these sort of questions when it comes to choosing stuff from other stuff. That is what binomial coefficients are all about. So let's get into a definition so that we can kind of get a better mathematical framework for this. So a set is an unordered collection of items called elements. I think this is best illustrated with an example. I can take a set, which I call A, for example, which can just be a set consisting of numbers 1, 2, 4, 5, let's say. Simple enough. And they don't have to be numbers. I can take a set B, and I can just have some letters here. A, C, F, G. We can also have sets of sets, right? I can take A and B that I've defined here, and I can make a new set C, I'll call, which includes A and B. There's also the empty set. So the empty set has a special symbol, which is this guy, and this is literally just the set with nothing in it. And we usually denote sets with these curly braces. And there's more complicated ways to define sets that you will see if you have taken any university level math. But for our purposes, this is totally fine. And the unordered part here is worth stressing for a second, because it means, for example, that A over here, this is the same as 2, 1, 5, 4. It's the same set. The order does not matter when we think about sets. And we have elements are just the things inside the sets. So we can say, for example, that 2 here is an element of A. This little f here is an element of B, for example. The empty set has no elements. So those are sets. And now we have the second definition. If A and B are sets, we say that A is a subset of B, and write it using this kind of curly less than or equal to symbol. That's how I like to think about it. If every element of A is also an element of B. So, for example, in our super example, A is not a subset of B. But, for example, we could define some new sets A and B. let's say A is 3, 5, and B is 2, 5, 3, 1. So in this case, A is a subset of B because each element of A, namely 3 and 5, is also an element of B. And this is often written down as like a Venn diagram. So if you have A, which is like this small set, that's contained in this bigger set, this is kind of the image that you have for A being a subset of B. Okay, perhaps you can guess where this is going. So let's look at our earlier question that you're forming a student council where you want to pick 3 students and there are 5 nominees. How many different councils can you make? This is equivalent now to this mathematical statement. How many 3-element subsets of a 5-element set are there? So if you recall, we had our 5 nominees, which we labeled A, B, C, D, and E. So the set here, for example, we can just call it maybe N for nominees. So we have A, B, C, D, E. And we want to find subsets which are 3 elements large. And these 3-element subsets, for example, just as an example, we have the subset BCE. This is a subset of N. This is a possible council, right? So this 3-element subset is a council. And finding a number of councils is then equivalent to just saying how many different 3-element subsets can we construct from N, or really from any 5-element set. Okay. And because we answered this already, we already know the answer to this is 10. Okay. So let's generalize this a little bit. We have this definition. The number of k-element subsets of an n-element set is denoted by this, which can be read as n choose k. And these are called binomial coefficients. Okay? So you have some set with n elements. You could imagine 1. Let's just say it's the numbers up to n. Doesn't have to be. And you want to find some subset of it which has k elements. And you want to find the number of ways that you can do. So, for example, 5 choose 3. Well, let's read out the definition, right? What is 5 choose 3? So 5 choose 3 is the number of k-element subsets. Well, I guess here k is 3, so I'll write 3. 3-element subsets of a 5-element set. Okay, but what did we just do up here, right? The number of 3-element subsets of a 5-element set, it's 10. So 5 choose 3 is 10. Okay. So that's our first binomial coefficient that we have computed. It's far from the simplest binomial coefficient you can compute. It's also definitely far from the most complicated. Okay. 4 choose 2. Now we're being a little more abstract, but let's just do the calculation, right? Let's say we have 4 elements, 1, 2, 3, 4. Again, it doesn't have to be the numbers 1 to 4, but I think it's a convenient thing to do. How many can we construct? Well, let's just list them out. We have 1, 2, we have 1, 3, we have 1, 4. I do think organizing the data in this way makes it easier to keep track, by the way. You can try to just rattle off subsets however you like, but having it organized makes it a little bit easier. So you have 1, 2, 1, 3, 1, 4. You have 2, 3. You have 2, 4. And you have 3, 4. That's all we can do. So 4 choose 2. Just counting these off. 4 choose 2 is 6. Okay. So this is the definition of binomial coefficients. This is how they are. So you can guess that this is essentially defined for any non-negative n and k, which are integers, right? Okay. So I think that's all for this time. Thanks for watching. I hope to see you for part 2.